Okay, so exam number 2, problem 1, is actually a homework problem. Okay, it'll hand you in 6.29, although I simplified it by replacing the last two questions, C and D, in the homework problem, which were complicated. You had to find minimum, maxima, take derivatives, etc., which I didn't want to have you do an exam with some simpler questions. But the first two parts were identical. Okay, and this is where you're pushing a book against a wall, pushing it at an angle theta, and you are holding the book, but just barely. Okay, and that is going to be a key phrase when we get down to this problem. But in any case, to get started with problem 1, you're asked to draw the free body diagram for the book. And so we're concentrating on the forces on the book. That's the book. Of course, there's the force you're pushing at, F. That is an angle theta with respect to vertical. Okay, there's gravity acting down, mg down. It's against the wall, so there's a normal force perpendicular to the wall pushing on it. And there's a force of friction. Now, if you didn't have that word barely in it, you wouldn't know if the force of friction is up or down, because you have the word barely. In fact, the force of friction is assisting you, because if you pushed any more lightly, the book would fall. So the force of friction is acting up in this case. So those are the four forces, and you need a coordinate system. So I'll just draw an XY coordinate system like this. So we have gravity down, normal force pushing against the book perpendicular to the wall. The force you're pushing at, I'll just call F, and the force of friction going straight up. That's your free body diagram and the coordinate system. Okay, next is and that's part A. Next in part B, it says calculate the magnitude of the minimum push you must exert. Okay, that's asking you for a push, so you should realize that this is a Newton's laws problem, plus you've seen it before. So you need to get the components of the forces and write down the components of Newton's second law. So the sums of the forces in my x direction are F, and hopefully you can see that it'll be F sine theta, the opposite sine theta is opposite of our hypotenuse. So I'll have a plus F sine theta. Okay, I've got a normal force pointing in my negative x direction, and that's it, because mg is down and ff is up. They don't point in the x direction. This has to be equal to the mass times the acceleration in the x direction, but that's 0. Book's not moving in the x direction. Okay, so this equals 0. So what I learned from this is that the normal force equals F sine theta. Okay, which isn't the answer, but it's something I've learned from it. I'll need the normal force when I go after friction, which you should realize. So now let's write the sums of the forces in the y direction. That's equal to, well, we have F cosine theta will be in my positive y direction. And we have gravity down, and we have friction up. So it's going to be plus us, and it's static friction because the book isn't moving with respect to the wall. Those have to sum to 0 because it's staying at rest with respect to the wall. So let's just plug in for the normal force. We have F cosine theta minus mg plus us, and the normal force we know from up above here is F sine theta. And these have to sum to 0. Okay, so this is an equation. Remember, what you're asked for is the force you have to push with. And so I can solve this equation for the F, just leave both F's on the left side of the equation, which will give me an F cosine theta plus mu F sine theta. But I'll just keep that in mind for a moment. Take the mg to the other side, and then divide by the cosine theta plus mu static, I'm sorry. U static F sine theta. And that's it. That's my answer to part B. That's the minimum force that I would need to push at in order to have the book barely against the wall, where I use that mu static, or the force of static friction, is actually less than or equal to mu Sn. If I'm just barely holding it, then I'll rely on static friction. Okay, so I'll just make that an equality. Okay, so where does that leave us? That leaves us with C. Show that your answer for part B, this answer makes sense in the case where theta equals 0 degrees. Well, at theta equals 0 degrees, you're pushing straight up. If you're pushing straight up and not against the wall, friction isn't doing anything. You're supporting the weight of the book with your hand. So I'd expect that F would just become equal to the weight of the book. And in fact, that's what my equation has, because what we'll do here, with theta equals 0, that implies cosine theta equals 1 and sine theta equals 0. So my formula here becomes mg divided by 1 plus 0, or just mg. And that's what I would expect. Check mark. Okay, you're pushing straight up. With F equal mg. Okay, so I've shown my answer makes sense in that special case. But now there's another special case. So it's impossible, according to the answer for part B, to hold the book stationary against a frictionless wall. So frictionless says μs equals 0. Okay, if I'm pushing perpendicular, then theta equals 90 degrees, which implies cosine theta equals 0, sine theta equals 1, and what I have is F equals mg divided by cosine of 90 degrees, which is 0, plus, well, sine theta may be 1, but I've got 0 from us now, plus 0, so I've got mg over 0, which goes to infinity, which implies impossible. And if you've been paying attention in lecture, you might remember a demo where we did exactly this. I sprayed a wood wall Strohsacker with some wax and challenged a student to hold the physics textbook up against the wall, pushing at 90 degrees, and of course it's impossible. Okay, or at least very hard. That's because we can't actually get theta equal to theta equal to 0. I'm sorry, can't get mu, static friction, equal to 0, even with wax. So that's problem 1 on the exam.